Now, let us take a look of our third problem, how to select the kth smallest item from a set of n items. So again, we assume that the input is an array S of n numbers. So a straightforward method is to repeatedly finding the minimum. So we find the first smallest item, remove it, find the next smallest item, remove it, find the next smallest item, remove it, and so on and so forth. So after doing this for k times, then we will be able to find out the kth smallest number. Now the number of comparisons that we need will be order of k times n. This is actually not a bad idea, so it will give us order n time when k is a constant. But on the other hand, it could really go bad when k is large. So for instance, when k is equal to n over 2, so we want to find out the number that stands in the middle, so we call this the median. In that case, using this method, we would need n squared time. And if we need n squared time, then perhaps we should have sorted all these n items from the beginning. And then, after sorting the n numbers, then we'll be able to find out whichever k that we have for the kth smallest number. Now, in particular, we are interested in this case. So can this process, can finding the kth smallest item be done using linear time only for any k? Okay, so let us take a look of our first idea. So we are going to make use of the partition idea that we are using for solving quicksort and apply this here to find the kth smallest item. Now the partition idea in quicksort was choosing a certain pivot P and dividing or partitioning the original n items into two groups so that we can make the original problem into smaller subproblems. And for this, finding the kth smallest item, after we choose the pivot P, we partition the set S into S small and S large. S small contains those smaller numbers, smaller than P, and S large contains those larger numbers, each number larger than P. Now, during this process, during this partition process, we can actually count the size of S small along the way. And let us call Z to be equal to the number of items smaller than P. Now, depending on the value of Z, we could have different things to do. So for instance, if Z, this value Z is equal to k minus 1, that means that there are exactly k minus 1 numbers smaller than P, then what does that mean? It means that P will be the kth smallest item. So in that case, we will simply return P. Now on the other hand, if this set is greater than or equal to k, that means that there are more than k numbers in this group S small. Then the kth smallest item must be now inside this S small. So what we are going to do is we are going to find the kth smallest item in this S small. And then there could be the third case. So when Z is smaller, so it's not like this and it's not like this. Is that okay? So in that case, when Z is smaller than or equal to k minus 1 or whatever. So in that case, what we know here is that the kth smallest item of the original set S must be inside this group S large. But on the other hand, it is not the kth smallest item in S large. It is going to be k minus Z minus 1 smallest item in S large. So we are going to find this smallest item in S large instead. So what we see here is that after doing this partitioning step, we are going to have either the problem solved immediately, or we are going to 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 get a smaller subproblem and then solving the smaller subproblem instead. Now let us use Tn to denote the running time of this method. In the worst case, what could happen? In the worst case, the pivot is so bad that we are not partitioning things at all. So we will make all the numbers into the same group. So in that case, T of n is equal to, we spend n operations, n comparisons, or roughly order n comparisons to do the partitioning, but then we are reduced to only a problem of size n-1. So we still need to spend T of n-1 to solve the problem. Now solving this recurrence, we will have Tn is equal to theta of n squared. So this is really bad in the worst case. But on the other hand, if the pivot P is chosen randomly, we can show that, but not in this class, okay? So if you are interested, you can show that with high probability, the running time is only of theta of n. So this method is quite efficient in the sense that, let's say 99% of the time, it runs in theta of n time. And also, not just 99% it's theta of n, the expected running time is also theta of n. Okay, so although there are cases where it is bad, like n squared, but it won't occur frequently, and on average it is of theta of n. So making use of this partition idea actually is not bad. But we are somehow, like, we want to ask further, can we still do better? Now, if we want to do better, let us check what was the problem in the current method. Now, when we are doing the partitioning, the item P that we choose may not be a good one, so it may partition S very unevenly. So if this is the case, then it will leave us with a large subproblem. A large subproblem will mean that we will still need to spend so much time in solving this large subproblem. So here, what we are going to do here next is we will show how to find a good pivot P. But we will sacrifice some time, so we will spend some extra time, but we will guarantee that we will find a good pivot P. So how good is this pivot? So this pivot P will allow the subproblem size to be bounded, and it is bounded by at most 3/4 of the original. So 1/4 of the original numbers will be removed in the subproblem. Okay, so we are going to guarantee that we are going to take away a lot of numbers into consideration during the computation of the subproblem. And after doing this extra time, the reduction in the problem size allows us to bound the worst case time to be order of n. So let's see how we can get a good pivot and what is the corresponding extra time and how to bound the total time. Okay, the idea here is called the median of medians. So what we are going to do here is, let's have the original set S partitioned into groups. Each group has 5 items. So let's say there are altogether n items. So we are partitioning them into the first group with 5 items, the second group with 5 items, and so on and so forth. Now we are going to sort each group separately. So we are going to sort these 5 items. Find out who is the smallest, who is the next, who is the middle, who is the fourth, who is the largest. And we also sort this group, and so on and so forth. Now notice that each group contains only a constant number of items, so the running time does not depend on n. So to sort the first group, the running time is order 1. To sort the second group, the running time is also order 1. So each group can be sorted in order 1 time. The total to sort all of them is still order n time. Okay, now we are sorting the groups one by one. When we have the groups, we will know what is the median of each group. what is the item that is standing in the middle? Okay, so we have two numbers that are smaller, two numbers that are larger, and the median that stands in the middle. And then let us consider the median of these medians. So in the previous page, so here we will have a lot of medians, right? So now how many medians are there? So there are n over 5 groups. So altogether there are n over 5 medians. And we want to look at, among all these n over 5 medians, which one stands in the middle. So we forget about the pink one, we forget about the purple one. We focus on the orange one, the median. And then we want to find out, among all these medians, what is the median of these medians. So we call it M. Okay, so roughly speaking, we can have the certain group that contains the median of the medians, and then let's place all the other groups with smaller median on the left side, and all the other groups with a larger median on the right hand side. Okay, so this is what we see. And now we claim that this median M is actually a very good pivot. So let's see why this is good. So let us focus on this median of medians M. We will see that these two numbers are smaller than M, because this is in the same group, right? And the medians of all the left side group are smaller because this is the median of the medians. So these are the smaller median. And for each of these group, the pink balls are smaller than the median. So if this pink one are smaller than this pink one will be smaller than M. So in the figure that we see here, all those balls that are marked with the cross will have value smaller than or equal to M. There could be more. They could still be having value smaller than or equal to M, but we don't care. What we care here is that at least those marked with the crosses are numbers with values less than or equal to M. So we will know that they are guaranteed to have some numbers that are smaller than or equal to M. And similarly, we can also show that at least n over 4 numbers will have values larger than or equal to M. Now these two things, so this one, at least n over 4 numbers are smaller than or equal to M, and at least n over 4 numbers are larger than or equal to M, is something that is good for this M to be chosen as the pivot. It is because if we use M to partition S, then the size of S small cannot be too large because we are guaranteeing that a lot of numbers are larger than or equal to M. So S small will have size at most 3n over 4. And similarly, S large will also have size at most 3n over 4 because we guarantee a lot of numbers are smaller than or equal to M. So S large cannot be very large. S large can only contain at most 3n over 4 numbers. So the median of medians M will be a good pivot. The drawback here is that it is unlike the previous random pivot selection. We will need to spend extra time to get this M. So let us analyze the running time of using this method. Okay, so to recap, this will be our new approach. So in the first step, instead of choosing the pivots randomly, we will find out what is the median of medians and then use this as the pivot. After that, the other steps are the same. We are doing the partitioning by P, count the size of S small. Depending on its size, we either return P or search for the desired value, the desired item in the S small group or in the S large group. Okay, now for step 1 in the previous this method, this is finding the median of S. So it is finding the median of medians, right? So it is the problem of what? It is the problem of finding the median from n over 5 medians. So this is exactly the same type of problem that we are solving, selecting a particular smallest item from a group of numbers. So for step 1, we are going to apply recursion in order to find the median of medians. So here, let us use t prime n to denote the running time of this method 2. Now in the worst case, so we are analyzing the worst case, okay. Now t prime n can be decomposed into the time for doing step 1, the time for doing steps 2 and 3, and the time for doing step 4. Now step 1 is the median of medians. So how much time does it take? So it takes order n time to find out to get the partitioning of the S into groups of 5, and then find the median of each group. So there are going to be n over 5 medians results. So it takes only n time to do the things up to this point. Now among the n over 5 median, we want to find the median of these medians. So this is a problem of selecting a certain smallest item in a group of n over 5 items. So the time that we need will be t prime of n over 5. So this is the running time for step 1 only. Now for step 2, this is the partitioning step. So we have already obtained the pivot. So it takes order n time to do the separation and also to compute the size of S small. And finally, this is the last step. Now, the last step here is either we are doing this very quickly, taking constant time, but in the worst case, we will be searching S small or S large. But we are not going to search both of them. We are going to search either S small or S large. And to search S small or S large, it won't be a difficult problem because the size of them is bounded by 3n over 4. So the time to do the searching in step 4 is at most t prime of 3n over 4. So this is the new recurrence for the time for the second method. And then it turns out that t prime n is equal to theta of n when we are using the recursion tree to help us to expand these terms. Okay, so what does that mean? By spending this extra time, this is the t prime n over 5 and the n, these are the extra time, we get a good median of medians as the pivot. And this allows us to change this part to 3n over 4 instead of n minus 1 in the previous method. So altogether, the extra time is worthwhile, and then we can bound the overall time to be theta of n. That's all for this lecture. Thank you.